Hello, and welcome to Agrosive Physics. Today is day 56, and what I'd like to do today is concentrate solely on problem solving. We're going to look at level 2 problems today. And level 2 problems might involve drawing a free body diagram, or possibly finding the net force on the objects first before we calculate for the centripetal force. Now remember, every time we're doing a free body diagram, we're going to draw all the forces acting on the object. Then we're going to sum up the forces in the direction of motion. But remember, with centripetal acceleration, or centripetal forces, the force is always going to act to the center. So what that may mean is that instead of setting the forces equal to ma, we're going to have to set it equal to mac, or mv squared over r. So in this case, free body diagrams are going to still be useful, but instead of doing the sum of the forces equals ma, that a is going to be v squared over r because we're dealing with circular motion. So these would be level 2 problems, a little more complex, but using skills you've already learned in the forces section. Free body diagrams perhaps, maybe even using friction. And remember, when we solve for any of the forces involved, they're going to act towards the center of the circle. Now, the center of the circle is going to be our positive direction because that's where the forces want to act in order to keep the object in the circle. And any force that opposes that will be negative. So inward will be positive and outward will be negative for these types of problems. But for now, let's look at some practice problems. We'll take out the whiteboard and solve some problems now. Thank you. All right, our next problem involves a penny on the edge of a 12-inch vinyl record. And some people may not be familiar with the record themselves. This is a 12-inch vinyl. I actually measured it. It's a little shorter than 12-inch, but I guess they round up to 12. Possibly some of the other vinyls are a little bigger. But this is considered a 12-inch vinyl, so the diameter is 12 inches. I'm going to take a penny and I'm going to place it on the edge. Now, record players have different speeds, and they're either, well, you have three major speeds. You have 33 1/3, which spins the 12-inch like this, and that 33 1/3 represents the revolutions per minute. And then you have a 45, and sometimes even a 78. And all the numbers represent revolutions per minute. So in this case, what we're going to see is if I place this penny here, and I have the record spinning, and of course I can't have the needle on the record or else it's going to run into the penny, will the penny fly off? And I have to estimate a few things. First of all, I needed to know the mass of the penny. And second of all, I needed to know what the coefficient of friction was going to be. Now, effectively, here's what's going to happen. If this is our record, the penny is sitting here, and of course this is not to scale. The penny is going to have gravity pulling down on it. It's going to have a normal force pulling up on it. And then if it doesn't slide, it's going to have an inward force, and that inward force is going to be friction. Now, if we think about it and we're looking at it from the side, friction is the centripetal force. So here's what's going to happen. I'm going to try to find the friction that is maximum for static for the 33 1/3 and then for the 78 and compare it to whether or not it will slide off. So the static friction is going to be what I look at first, and then I'll find the centripetal force at each of the speeds. Now, the other issue is, well, what's the mass of a penny? And what I had to do is, I don't have my balance here at the compound. So what I did is I looked online, and it said that any penny made after 1985 has a standard mass of 2.5 grams. So we're going to use that value because I found a nice, well, not very shiny, old penny from 1985. And to me, that's relatively, well, that's not too old, but to you, that's before many of you were born. But I was about 10 years old at that point. Now, bottom line, we have our free body diagram here, and what I'm going to do is place in the box the mass. Now, this is in grams, so I'm going to bring it 3 places to the left, 0025, and that's going to be in kilograms. Now, that being said, force of gravity is mg. So 0.0025 times 9.8. I use my calculator for that. 0.0025 times 9.8 gets me 0.0245 newtons, which, because it's flat, is going to be the same as the normal force. Now, friction is mu Fn, and in this problem it says, and this is where I had to estimate a little bit, we have a penny located at the edge of a 12-inch vinyl record which acts the same as steel. Now, of course, vinyl and steel are different materials, but we happen to have copper versus steel on our reference table. And of course, the penny isn't even completely made of copper anymore either. So copper on steel has two values. It is 0.36 for kinetic and 0.53 for static. Now here's the question. Do we use the kinetic or the static? And what's interesting is that although the penny is going to move tangent to the circle, the whole point of friction inward is to keep it from moving. And we're actually going to try to find the static friction. So I'm going to use 0.53 and the 0.0245 newtons. Now if I do that, 0.53 times 0.0245, I get 0.013 newtons. And what I'm going to look at is whether or not the centripetal force is greater than or less than 0.013 newtons at 33 1/3 RPM, and then again at 78 RPMs. So this is going to be my conditional, C-O-N-D-I-O-T, conditional. There it is. Statement. So I'm going to compare my answers to that. Now, how do you find the centripetal force? Well, that's mv squared over r. The mass we have, it's 0.0025. The v is going to be different, and the radius is going to be standard. The problem is we have a 12-inch vinyl record. So 12 inches is the diameter, which means we have a 6-inch radius, and we have to look up 1 inch is 2.54 centimeters. Cross out the inch. Let's calculate. We have 15.24 centimeters, which I'm just going to convert directly to 0.1524 meters. So that's our radius. Now, mass we have already. I'm just going to write that mass, 0.0025 kilograms. Now, the speed is the distance over time, which is circumference, 2 pi r over t. So 2 pi times 0.1524 meters. Okay, now what's the t? Well, we have 33 1/3 RPM, and the PM means revolutions per minute, which is 60 seconds. So if I take 60 and divide it by 33.33, I get 1.8 seconds. So the time period is 1.8 seconds. Now it's 78 revolutions per minute. We have 60 divided by 78 in this case, and we have 0.77 seconds. So this one was 1.8 seconds, and the other is 0.77. So what we have is two different solutions we're going to look at. Now, first of all, if I do the V here, I have 2 times 3.14 times 0.1524, all divided by 1.8, and I have 0.532 meters per second. And then if I have this one, it's 2 times 3.14 times 0.1524 divided by 0.77 seconds, and I have 1.243 meters per second. Now, at this point, we need to figure out which centripetal force is going to be greater than or less than the .013, which is the maximum static. This was the static friction. Well, if I go back to my centripetal force equation, it's 0.0025 kilograms times 0.532 meters per second squared, all over, radius is 0.1524 meters. And I'm going to do the same for the other one, 0.0025 kilograms times 1.243, all of it squared, over 0.1524 meters. All right, let's find the centripetal force for the 33 1/3. 0.0025 times 0.532 squared divided by 0.1524, and I'm getting 0.005, so 0.005 newtons here. And then for the other one, 0.0025 times 1.243 squared divided by 0.1524, I have 0.0253. 0.0253 newtons. All right, let's look at this. If we have the maximum static friction to be 0.013 newtons, the first speed is under that. The second speed is over that. So that means 33 1/3 will stay on, and then 78 will fly off, because the static friction is not large enough to overcome this centripetal force. In this case, friction needs to be that centripetal force in order to keep it on the record itself. Well, there you go. Very complex, but very interesting. Okay, for our next problem, we're going to look at a car traveling along a road. It's going to go down into a valley and up over a hill. And the hill and the valley have different radii. Now, the car is traveling at 40 miles per hour. So let's just get rid of that right away. 40 miles over hours. 1 mile, 1609 meters. 1 hour, 3,600 seconds. Miles will cancel. Hours will cancel. We're left with meters per second. So 40 times 1609 divided by 3,600 is 17.9 meters per second. Now, the car also has a mass of 1,200 kilograms. So I'll just put that here. I'm not going to fit it in the box that I drew. Speaking of boxes, we're going to need to draw a free body diagram. And I'll start with the bottom over here. The free body diagram is going to look like this. You have 1,200 in the box, the normal force going up, and gravity going down. Now, normally, gravity and the normal force are the same. But because we're experiencing centripetal motion here, circular motion, it's going to have a different value. That centripetal force is going to contribute to the normal force as well. In some cases, it'll add to it. In other cases, it will subtract. So what we're going to have to do is set up our equation where the one pointing to the center, in this case the normal force, because the car is going to be sitting here, is going to be the positive, and gravity is going to be the negative. So Fn minus Fg equals mv squared over r. Well, let's find Fg. You're going to do 1,200 times 9.8, and you have 11,760 newtons. So you have Fn minus 11,760 equals, mass is 1,200, the velocity is 17.9 meters per second, quantity squared, and then we divide that by the radius, which is, for the first hill, 10 meters. So I'm going to take care of this term first. 1,200 times 17.9 squared divided by 10. And that term is going to be added to the 11,760. So plus 11,760, end up with a normal force of 50,209.2 newtons. At the top, it's going to be slightly different. The free body diagram is going to look the same. In fact, if I draw the top here, normal force up, gravity down, 1,200 in the box. But now if we're sitting at the top of the circle, gravity is the one that's going to be inward, so that's going to be my positive. So Fg minus Fn equals mv squared over r. The slight difference is that the radius is a little bigger for the second one. So 11,760 newtons minus Fn equals 1,200, 17.9 meters per second, quantity squared, over 15. So what we're going to do now is actually subtract that term from 11,760. So 1,200 times 17.9 squared divided by 15, and we're going to subtract 11,760 minus second answer. The normal force is a negative 13,872.8 newtons. Well, what does that mean? What it means is at the top of that hill, if the car is traveling at 40 miles per hour, it's going to actually leave the ground and fly off the hill. So it will not even have a normal force because it's in the air. So what we're going to do is continue this problem, because this is an abnormal solution here, and let's try to find what speed will it take for that car to leave the ramp, to leave the hill and fly off the road, because 40 miles an hour is way too fast. So let's find a safe speed that the car should have been traveling to not do that. As we revisit this problem, we're going to see that the car had a significant normal force at the bottom. In fact, it can't fly off the hill at the bottom of a valley. But then when we get to the hill, it was traveling way too fast, and 17.9 meters per second exceeded the speed that would keep it on the hill. So let's figure out what it would be to barely leave the hill, and then anything less than that will be safe. Well, if an object is approaching this point and then starts to fly off the ground, that means the normal force approaches zero. So what we'll have is a situation where if we calculate the speed at which Fn is zero, then anything less than that will be safe, and anything greater than that will be dangerous. In this case, Fg minus Fn, because Fg was towards the center, equals mv squared over r. And we're going to say the normal force approaches zero, so that term disappears. So it simplifies to 11,760 equals 1,200 v squared over 15 meters. And we could solve for v. What is the speed at which the car will leave the hill? So I'm going to cross multiply 11,760 times 15. I'm going to divide by 1,200, and then I'm going to take the square root. And I'm getting 12.12 meters per second. So we exceeded that by over 5 meters per second. And because of that, we ended up calculating a negative normal force. You can't have a negative normal force because it needs to be positive if it's pushing against the ground. So in this case, if we were traveling at 10 meters per second or 11 or even 12 exactly, we would still be touching the hill. But at 17.9, we would fly right off the hill, and then it would become a projectile motion problem.